Good morning, friends. It gives me immense pleasure to be here again for aircraft stability and control, and today Perturb pitching moment. I am going to cover these topics: Perturb pitching moment, alpha derivatives, q derivatives, and Perturb longitudinal equations of motion. So here we have done with the following derivatives in my previous class. Dou z by dou u by u1 at steady state is equal to minus qs 2cl1 plus clu, and in this clu, if we draw, this is the m and this is the cl. This clu will be like this. So this is the dou cl by dou m is equal to 0, and if dou cl by dou m is greater than 0, it is a transonic, and this is the sonic, and this is the subsonic. Okay, so this gives this one. Now next we have drawn that alpha derivatives. Dou fz by dou alpha is equal to minus q1s, here cd1 plus cl alpha. Here drag at steady state, if you know, and if you know the cl alpha, we can find out this alpha derivatives. And also fza q is equal to half rho v square s clq qc by 2 u1, and dfz by dou qc by 2 u1 is equal to minus q1 s clq. Similarly, we can also find the alpha dot derivatives. So for alpha dot, the force fza alpha dot is equal to half rho v square s cl alpha dot c by 2 u1. So here if we differentiate this with respect to alpha dot c by 2 u1, then this will be 1, and here this is half rho v square. So here I will get minus q1 s cl alpha dot. Here minus sign is q in anti-clockwise direction. Okay, this I have explained already in this diagram, that when it is plus q, then this will generate a minus cm, okay, in opposite direction. So now to work for equation of motion in perturbed condition, we know that fz is equal to fz minus mg theta sine theta 1 is equal to m w dot minus q u1, which we have done earlier. Now putting fz from above equation a here, so now this dfz by d alpha is equal to minus q1s cd1 plus cl alpha. So now dfz by d alpha is equal to minus q infinity s cd1 plus cl alpha. So new equation in fz will be in this way. So perturbed equation of motion in fz will be now m w dot minus q u1 is equal to minus mg theta sine theta 1 plus q1s minus clu plus c2 cl1 u by u1 minus qs cl alpha plus cd1 alpha minus q1s clq qc by 2 u1 minus q1s cl alpha alpha c by 2 u1 minus q1s cl delta e into delta e. It is a total fz. Now we have to see moment equation in perturbed condition for pitching, that is longitudinal case. So moment equation m is equal to I y q dot. We know that moment is a function of these terms. F is this moment is a function of u by u1 alpha q alpha dot into delta e. So we can write in the expanded form by using Taylor series. So here we have used the Taylor series and we have made this equation as shown here. In all the parameters are given. So we need to find out each derivative, first starting with dou m by dou u by u1, the first case. So here we know that m is equal to half rho u1 plus u square s cm into c bar. So now to find dou m by dou u by u1, so half rho v square s 1 plus u by u1 whole square c bar cm. So here half rho u1 square s c bar 1 plus u by u1 square cm. So now if you differentiate this with respect to u by u1, we will get here q infinity s c bar 2 1 plus u by u1 cm. We have to differentiate this 1 plus u by u1. We will get 2 1 plus u by u1 plus q infinity s c bar dou cm by dou u by u1 1 plus u by u1 square. So here this infinity will be 1 as a subscript for steady state condition. Okay, so here we got for steady state u is equal to 0. Then we get that dou m by dou u by u1 is equal to 2 q infinity s c bar cm plus q infinity s c bar dou cm by dou u by u1. So here all infinity will be here 1. So 2 q1 s c bar cm 1 here steady state, and here q1 s c bar dou cm by dou u by u1. So cm at steady state is equal to 0 as it is trimmed condition. So here dou cm by dou u by u1 is equal to m1 dou cm by dou m. Okay, here m is a Mach number. So here this will convert to, this will be the Mach number. So m1 dou cm by dou m. Okay. At low speed, the aerodynamic center of the tail is at c by 4 or at 25% of the chord. So aircraft aerodynamic center shift backward as speed increases to supersonic regime. This shift in aerodynamic center due to the supersonic condition increases the moment arm LT of the tail. This you can see at in this diagram. For the subsonic case it is LT, but as the Mach number is increasing, this will increase to here. So this LT new will be more than LT. So the moment arm is increased, and so the moment will be more for this case. This increase in moment arm LT will increase the coefficient of moment Cm and makes pitch down tendency due to acceleration. This is known as a tuck under. Very nice concept. It is called the tuck under. Means as and when the Mach number is increasing, the aerodynamic center of the aircraft or the aerodynamic center of the tail will go backward, and so LT, the distance between aerodynamic center and the center of gravity of the aircraft, will increase. As this thing is increasing, then the coefficient of moment produced by the tail will be in the negative and nose will try to go down. So this phenomena is called the tuck number, and this derivative is called the Mach tuck derivative. The derivative dCm by dou u by u1 is called the Mach tuck derivative. It is due to the additional delta Cm produced due to increase in velocity or speed of the aircraft due to supersonic case. It is extremely important, and lot of incidents and accident happen due to this phenomena. So dou m by dou u by u1 is equal to 2 q1 s c bar cm plus q1 s dou cm by dou u by u1. So this is m1 dou cm by dou m. So negative for supersonic speed. So this parameter will be negative for supersonic speed. You have seen that dou m by dou u by u1. So now dou m by dou alpha is equal to q1 s c bar dou cm by dou alpha, and dou m by dou qc by u1 is equal to q1 s c bar cmq, where m is equal to half rho v1 square sc cmq qc by 2 u1. Now, so we have to see the alpha derivative. So this m is equal to half rho v1 square s c bar cm alpha alpha dot c by 2u1. So dou m by dou alpha dot is equal to q1 s c bar cm alpha dot. So same way for the delta E derivatives. So m is equal to half rho v1 square sc cm delta E into delta E. So dou m by dou delta E is equal to q1 sc cm delta E. Now how to estimate total moment? To estimate the total moment, we have to put this value, all these derivatives here and add up. So till now we have developed all the derivatives and we put then this value, we get the total moment. So dou m by dou E is equal to q1 s c bar cm delta E. We know that cm delta E is equal to minus cl alpha t vh nt neta t and tau. So once I know all the derivatives, I can get equation for q dot, and this q dot is equal to mu dot u m alpha dot alpha mq dot q m alpha dot alpha dot m delta E into delta E. Here mu, mq, m alpha, m delta E are dimensional dimensional derivatives. Our next task to develop equation for u dot and w dot. These expressions will be developed, and w dot, the expressions is partial derivatives, and an aeronautical designer, we must know these u dot and w dot clearly. The Laplace transforms will be helpful to solve these differential equations that we will be learning soon. Okay, these are the references which I am going to refer, and thank you very much for joining the classes. Hope you will join the class, next class, and it will be very interesting for you to join the class.
Like, share and subscribe. Hit the bell icon for more updates.